Okay, welcome to the 32nd International Conference on Formal Power Series and Algebraic Combinatorics. My name is Eli Bagno. Today, we'll have three speakers. Each talk is 25 minutes long with 5 minutes in between for questions and a short break. There will be a coffee break at the end of the session if you have time to stick around. Everyone is welcome to participate. The chat monitor for today is Amy Pang. And now I want to introduce our first speaker, which is Laura Colmenarejo from the University of Massachusetts, Amherst. She will speak about an insertion algorithm for diagram algebras.
Okay, so welcome everybody. Thank you very much for the opportunity of talking in this conference. And I want to present a joint work with Rosa Orellana, Anna Schilling, Franco Saliola, and Mike Zabrocki on an insertion algorithm for diagram algebras. So the goal of what I want to present today is that we want to explore a variant of the RSK algorithm with three main ideas. The first one is that we want to insert multisets instead of just integers. The second idea is that we want this RSK algorithm to modelize somehow diagram algebras, and we want it to be well behaved with respect to restricting to subalgebras. So the outline of the talk is gonna be the following. We are gonna have two parts. In the first one, I'm gonna kind of rediscover the RSK algorithm. And in the second one, I'm going to give some applications to the partition algebras. So the RSK algorithm has the following main idea. It's a one-to-one correspondence between some initial input and then two pairs of sets of tableaus. And I'm indicating here tableau 1 and tableau 2 because these two sets doesn't need to be the same, although it sometimes happens. And the reason why it's called an RSK algorithm is because of three mathematicians. For the R, we have Robinson, who in 1938 presented the one-to-one correspondence between permutations in a set and pairs of standard Young tableaus of the same shape here. A few years later, in 1961, Schensted generalized from permutations to words in the alphabet 1 up to n that I'm going to denote with brackets of length L. And instead of having pairs of standard Young tableaus, one of them is now going to be the set of semi-standard Young tableaus of shape lambda, again, the same shape between them. And the entries are going to be in the alphabet 1 up to n. And a few years after, Knuth generalized to generalize permutations over two different alphabets of length L, and in this case, we have both of the sets of tableaus to be semi-standard Young tableaus, each of them with the corresponding alphabet, but both of them with the same shape. So I want to give you an overview of the RSK algorithm, and I'm gonna do it initially with generalized permutations. So the main idea that I need to define a generalized permutation is that I need to have two ordered sets are gonna be totally ordered. In the previous slide is what corresponds to K and N. And I'm gonna define a generalized permutation from A to B as a two-line array. I have elements of A in the first row and elements of B in the second row. And I'm gonna order it in such a way that the elements in A are weakly increasing, following the order of A. And every time we have two elements on the top row that are equal, then I'm gonna order with respect to the order in B. And I just wanted to make sure that we are on the same page when it comes to the tableau. So the semi-standard Young tableaus of shape lambda in N is I'm gonna take the shape lambda, I'm gonna draw the diagram with the boxes. I'm gonna fill it with numbers in the alphabet 1 up to N. And the semi-standard part is saying that the columns are strictly increasing and the rows are weakly increasing. And I'm gonna be using French notation. So instead of just giving you the RSK algorithm, I'm gonna do it with an example. So I want to show you that if I consider this generalized permutation, which has length 13, and I have the alphabet 1 up to 6 on the top row and 1 up to 5 on the bottom row, we are gonna get these two semi-standard Young tableaus. So the main idea of the RSK is that we are gonna row insert the bottom row, and we are gonna record the top row. So let's just start with the generalized permutation. So it's color coding. So I need to insert the 1, and I'm gonna record the 1. So since I was starting with the empty tableau, then I just have these 1 boxes. So now I have to insert the next one, and the way I'm presenting it is I'm gonna keep the previous insert tableau on the left, and then I'm gonna see what I do insert and what I record. So I was having the 1 here, and I have to insert a 5. So I can put it next to the 1 in the first row with not violating the condition on the semi-standard Young tableau. I will just put it next to it, and I will record the 1. The next one is again 1, 5. So I have to insert the 5, and I can just put it next to it because I'm considering weekly increasing the rows. And then I just record the other one on the other side. And now the first interesting thing happens. I have to insert a 2, but now I cannot put the 2 next to the 5 because I will have 5, 2. So what I'm gonna do is I'm gonna put the 2 in the first place that I can. So I'm gonna have this 5 over here. I'm gonna bump it out. I'm gonna put the 2 here, and then the 5 is gonna go in the second row. Since there is no row, no box here, I can just put it directly there. So I will get this other one. So the 5 is bumping the 2 is bumping the 5, and the 5 is going to the second row. And this one over here is the new box. So I will record the 2. The next one, I have to insert a 3, and I have the same situation than before. So the 3 is gonna bump the 5, and the 5 is gonna go to the second row. Since I can put it 5, 5, then that's no issue. So I just keep it there. And let me do one more step to see how we can continue increasing the rows. So if I want to insert the 1, what I have to do is I have to bump the 2. But once I have the 2 in the second row, what happens is that this is gonna bump the 5, and the 5 is going to the top, to the third row. So that's why I get this one over here. And again, what I have over here is that the new box, and I'm gonna record the 3. So if you continue doing this algorithm for the rest of the generalized permutation, what you get is the one that I got at the beginning of the example. Now, this insertion algorithm has very nice properties when it comes to enumeration and representation theory. So I'm gonna back up a few years. I was giving you the algorithm with Knuth result, and I'm gonna go back a few years in time, and I'm gonna look at the Schensted algorithm. So what he did was giving a bijection between words of length k in the alphabet 1 up to n, and a pair of semi-standard Young tableaus and standard Young tableaus. Since this is a correspondence, a one-to-one correspondence, then we have an enumerative result that says that n to the k, which is the number of words that I'm considering in this set, is equal to the sum over the partitions of k of the number of semi-standard Young tableaus and the number of standard Young tableaus that I was considering. And what happened is that this enumerative result is related to representation theory. So let me show you for this example what the representation theory side looks like. So if I consider the vector space C to the n, and then I consider the tensor k times with itself, I'm gonna get B tensor k. And I can consider this as a model in which I have a GLN action on the left and an SK action on the right. So because of the double centralizer theorem and the fact that these two actions commute, then I can decompose B tensor k as a direct sum where I have a simple left GLN model on the left and a simple right SK model on the right. And the fact that both of these set and indexed by partitions is a particular case of the Schur-Weil duality, but it's also it also generalized to the double centralizer theorem. And now what I want to do is, instead of like, I had in mind that we wanted to insert multisets. So what I want to do is I want to first rediscover the RSK in which I'm going to be considering multisets. So I was having this generalized permutation in my example earlier, in which like I have each of the entries on the line on the rows are just integers. And now I want to do a new encoding. So what I'm going to take is for every entry at the bottom, I'm going to record on the top the numbers that are equal. So for 1, I will have a 1 over here, a 3 over here, a 4, and a 6. So the number 1, I'm going to associate it to it, the multiset 1, 3, 4, 6. If I'm looking to 2, then I have 2 here and 6 here. So to number 2, I'm going to associate 2 and 6. And then, for instance, I don't have 4 here, so I'm just going to associate the empty multiset. And the way that I'm ordering, you remember I was having the set A and the set B. I need to order with respect to the top row, and I'm going to be using greater lexicographic order, which means that if the sets have different size, then I just order them according to the size. So I have empty, size 2, and size 3. But if they have the same size, then I'm going to order them lexicographically. And with this array, what I can do is I can just insert using the RSK algorithm that I described before. And then if I'm inserting the bottom row, I'm going to get a standard Young tableau with the numbers 1 up to 5 in this case. And when I record the upper row, the top row, what I'm going to get is I'm going to get a Young tableau in which the entries now are multisets. So just for the notation, I'm forgetting the brackets when I put the numbers in the Young tableaus. And then we can compare again how is this related to the previous, like the other version of the RSK. So with respect to the numerative results, if we are looking again to a Schensted, what we have is that the regular RSK was given this formula that I explained before. And now for the multiset version, we are getting n to the k again, but now I was having standard Young tableaus on the left, and I was getting a standard multiset tableaus of the shape lambda with entries in k on the right side. And there is a big difference here. I still have the same shape, but here you can see that I'm counting over partitions of k, which is the exponent, while here I'm counting over partitions of n, which is the size of the alphabet that I'm considering. And we can wonder if this formula resembles some representation theory result, and I can tell you that yes. Again, if we consider the vector space C to the n, and we consider the k tensor with itself, then we need some extra condition here, and is that n has to be, if n is at least 2k, then I can have a very nice decomposition of B tensor k as a S lambda, which is going to be a simple SN model, and this time active on the left. And on the right, I'm going to have this simple right PKN model. And I haven't introduced what is PKN, and that is going to appear soon. And this is the partition algebra. It's one of the diagram algebras that we are going to be considering. And the lambda bar here is obtained from lambda, and what I'm going to do is I'm going to just delete the first row. So the reason why we want to find a new variant of this, like if I think about this new version considering multiset, I'm still having sets like regular tableaus on the left side, and I want to do something different. I want to encode the partition diagrams, generalize permutations with multisets, and then I want the RSK to give me pairs of standard multiset tableaus. And I want this algorithm to be well behaved with respect to the subalgebras. Now, we are not the first one thinking about this kind of insertion algorithm. And I can say that our result matches the representation theory and the dimensions given by Halverson and Jacobson in 2018. But it also gives a new map from the standard multiset tableau to Bratelli diagrams that is different from the Penkart and Halverson result from 2017. And I will give some details on this last part, also with respect to one of the talks from FPSAC last year. So let me introduce what is the partition algebra and the diagrams. So the partition algebra is, as a vector space, is defined as the span over the complex of the set partitions of two alphabets. So the way that I'm going to differentiate my two alphabets is with regular numbers and numbers with bars. So it's called a diagram algebra because the elements in this vector space can be represented with diagrams. So in this case, I have as an example a partition algebra for k equal 8. So I have all the numbers from 1 up to k, 1 up to 8 here, and also the numbers 1 up to 8 with the bars. And what I have is that I have split them into blocks of numbers. And the diagram representation, what we are going to be doing is we're going to be putting the numbers 1 up to 8 on the top row and the numbers 1 bar up to 8 bar on the bottom row. And we are going to link the numbers that are in the same set, in the same block over here, in such a way that I just want to click to link them. I don't care how I do that. So for instance, I have 1, 2, and 4 link, and then I have 2 bar and 5 bar. So here I'm just like closing kind of like the cycle, if you think about it. 3 is by itself, so I don't do anything. And then the other cycle that I have over here is 5, 6, and 7. And then I also have 3 bar, 4 bar, 5 bar, 6 bar, and 7 bar. 8 and 8 bar are just 2 of them, so I just link them with a line. And 1 bar is also by itself. So I define the partition algebra as a vector space, but I can actually, I can extend it into an algebra just by multiplying diagrams. There is a very nice description of the multiplication, but we don't need it. So for I'm gonna save it. So in order to describe an RSK algorithm, I'm gonna look at these diagrams. I'm gonna split it into blocks. So let me introduce a couple of definitions. So a block is gonna be propagating if it contains vertices from both alphabets, if it contains numbers and numbers with bars. And if it's not propagating, it's non-propagating. So if we look at the example that we have over here, what we have is that 1, 2, 4, 2 bar, and 5 bar is one of the propagating blocks, while 3 and 1 bar are non-propagating. And in order to define the RSK, we're gonna kind of like order these blocks differently. So the first thing is to define the insertion algorithm is that I have a set partition on 2 alphabets, and I'm gonna order the blocks using the last letter order. That is, if I have 2 sets, I'm gonna look to the largest element in each of them, and I'm gonna compare them using that letter. So there is no grading part here. So I take my set partition and I'm gonna split it. I'm gonna have the propagating blocks that I'm gonna encode as a 2-line array. On the top row, I'm gonna have for each of the propagating blocks, the numbers that are without bars. And on the bottom, the numbers with bars. And I will give an example in a minute. And then what I'm gonna have is I'm gonna also order the non-propagating blocks in K and the non-propagating blocks in K bar. So I have this kind of like three sets of blocks. And the insertion algorithm, what we are gonna be doing is we are gonna first insert RSK. I'm gonna insert using RSK the propagating blocks. So I'm gonna get P and Q, which is just applying RSK to this 2-line array. And then we're gonna add in each of them, in P and Q, a row of empty cells followed by the non-propagating blocks. So it may look a little bit confusing at the beginning, so let me show you an example. This is a larger example compared to the one that I had at the beginning, but it shows very nicely. the algorithm. So I have here the propagating blocks. So I have 2, 3, 4, and 4 bar, 5 bar. So I will get this part over here. So I get 4 bar and 5 bar, and then 2, 3, 4. And then I have this other one. So I have 5 on top, and then 2 bar and 3 bar on the bottom, and so on. And in this case, the non-propagating blocks are going to be 7 and 8, 1 bar and 9 bar. And I will deal with them later. So also notice that we are ordering according to the last entry. So we have 4 is smaller than 5, smaller than 6, smaller than 9. I don't care how many elements are in the set. I just order by the last letter. So the first thing I do is apply RSK to this one, and I'm gonna get P and Q. And since I'm inserting the bottom one as the ones with the bars, and the top one is the numbers with non-bars. And then what we are doing here is we are adding a row of empty cells, and I'm gonna put the non-propagating blocks. So the number of empty cells that I have to put here is gonna be such that the total number of boxes is n. So as long as n is larger or equal than k, that's no problem, and I will have enough empty cells over here. So what this is telling us is that we have a projection between the set partitions, the diagram elements of the partition algebra, and pairs of standard multiset tableaus over the alphabet k bar and k. The numerative result related to this is that the number of set partitions and 2 alphabets is the bell numbers b to k. And then I'm summing over the partitions of n of the number of standard multiset tableaus of shape lambda with alphabet k. Now, one of the good points of this bijection, apart from other properties that it has, is that it's well behaved with respect to the restriction to subalgebras. So let me tell you what I understand by restricting to subalgebras. I was defining the partition algebra with diagrams, so I can impose properties on those diagrams. So for instance, if I want a permutation, I just have to link something from the top row with only one thing at the bottom. So if you see here, 1 is linked to 2 bar, 3 is linked to 1 bar, 2 to 4 bars, and 4 to 3. And there are other properties. For example, I can also look at matchings. Well, it's like represent like graph theory. I have everything is matched to something else, and that's all. But here I don't have the restriction of having something from the top row linked to something to the bottom. And the other property that appears in this one is a planar one, which is also coming from graph theory. And you can just like make sure that you can link things without having crossings. So if we add these conditions on the spanning set, then we will have subalgebras. And this table over here includes like some of those subalgebras. There are more, and our tables in the original paper contain more. But let me show you some examples. So what we have here is that, for instance, the group algebra is going to have as diagrams permutations, and this allows us to give the dimension. So these references over here, if you look to the original paper, you will see all the references included for each of them, but I just wanted to point them out here. So what happens is that we can, the same way that we characterize the subalgebra, the diagrams, we can also do it with the tableaus. So for each of those, we can, what we have done is we define a standard multiset tableau to be a matching tableau if there are some conditions over the sizes of the elements in the first row. For instance, we have that the first row only contains sets of at most 2 elements, and then all the other rows contain only elements of size 1. So for instance, this tableau over here is gonna be a matching. And we can also define a planar tableau, standard multiset tableau, by saying that it has 2 rows, and now the sets in the first row are pairwise non-crossing. This is a condition on the sets. And there is also a condition of all the elements in the second row with respect to the sets that appear. And this will be an example of being planar. And I'm running a little bit late on time. So let me tell you that what we have done is for each of the subalgebras, we can characterize the diagrams spanning the subalgebra and also the properties when you do the RSK algorithm that I just described. So that will be characterizing the number of entries, the sizes of the entries in the first row, and other properties like matching and planar that I just described. And then because of the correspondence and the fact that the RSK algorithm behaves well with respect to these subalgebras, we can give a result that compute the dimension of all the subalgebras. And if I were having more time, we can also use a branching rule result to give the dimension of the irreducible representation associated to each of the subalgebras. So here A sub k is the subalgebra, and SMT with the A sub k as a subindex is the standard multiset tableaus for each of the subalgebras. So these two results are giving us the enumerative result associated to the RSK algorithm that I just described. And this table of dimensions will keep all the information of the subalgebras, the dimensions, the index set of the irreducibles, and the dimension of the irreducibles. And I just wanted to add that we were mentioned last year and Tom Halverson talk, and this is one idea from one slide that he had, in which this represent the diagram algebra, the partition algebras. This is our RSK algorithm with English notation, and this is also related to the oscillating or vacillating tableaus described by Bencon and Halverson. But I want to point out that these are the ones.
Laura, please wrap up in the next minute or so.
Yep.
Okay.
So that's all.
Okay, thank you for this intriguing lecture. Now we have about 3 minutes for questions, and I'll turn things over to our chat monitor, Amy Pang.
There's been lots and lots of comments and questions on the chat, and lots of your co-workers have been answering. So just to pick a few, Francois Bergeron says, what about Q analogs of this extended RSK?
I haven't thought about Q analog of RSK at all.
Okay, related to that, yeah, what are you gonna say?
No, I was gonna say like for sure you can compute the Q analog of the dimensions, but I don't know what it means when it comes like do you want to label the tableaus or give a property? I don't know what that's like what he was having in mind.
Okay. Related to that, Dan Beter says, is there a Green's theorem or Schensted?
I don't know either.
Okay, there's another related question that says, did you look for local rules analogous to Fomin?
Analogous to?
To Fomin. Like this is from Martin Ruby.
So one of the properties that we have been looking to local properties. So for instance, if you flip the diagram upside down, you change you just flip it. That corresponds to switching the order of the tableaus. So that was one of the properties that we had for them that you usually have in the regular RSK. And we also have it in this case.
Okay. Maybe you can have time for one more. Nancy Wallace says, does this work with all partition subalgebras or only the ones with an a priori diagram spanning the subalgebra?
So we have only tried with the diagram ones. We also have the quasi-partition algebra that I wasn't including in the table. But I don't think we have tried with non-diagram algebras.
Okay.
Would be
Yeah, I
interesting.
guess. Yeah.
I think it would be very interesting to try with other algebras and see what happens.
Okay. Yeah, I guess it's time. So I should hand back to our host.
Thank you, Amy, and thanks again to Laura